Good morning. So, in the previous class, we completed the intensity of the Fraunhofer due to a single slit. So, we find out the intensity where I is equal to I naught of sine alpha by alpha whole square. Okay. Now, we have to calculate the intensity position, that is the principal maxima. First one is principal maxima. Okay. So, in this principal maxima, we'll explain that as the theta tends to 0 degrees, okay, when the theta d is equal to the 0 degrees, then it is known as the principal maxima, where r is equal to, from the above equation we know that r is equal to a sine alpha by alpha. Okay, r is equal to a sine alpha by alpha. Now take the common as a by alpha, then sine alpha in the exponential form or in the binomial expansion, we can write the sine alpha as alpha minus alpha cube by 3 factorial plus alpha power 5 by 5 factorial minus. So one sign will be minus and one sign will be positive for the sign, and all the odd numbers will be repeated. Okay, so as the sine alpha expression is this in the form of binomial expansion. Now if we remove the alpha as common, then in the denominator and the numerator alpha gets cancelled, then 1 minus alpha square by 3 factorial plus alpha power 4 by 5 factorial minus alpha power 6 by 7 factorial. So as alpha tends to 0, okay, if alpha is equal to 0, then the R maximum will be obtained. So for the higher intensity or the maximum intensity, then alpha tends to 0. Okay, then the theta value will be phi e by lambda sine theta phi e by lambda sine theta is equal to 0. As sine theta is equal to 0, theta also tends to 0. So this is about the principal maxima. Now about the secondary maxima. So just in this secondary maxima, we have to differentiate the intensity of the radiation. Okay, we have to differentiate the intensity of radiation with respect to the alpha. So d by d alpha of, what is the I value? So a square sine alpha by alpha whole square is equal to 0. Now if you differentiate the sine alpha with respect to the alpha, what we get? A square into, that is sine alpha by alpha whole square will be there. So for that we will expand in the form of 2 sine alpha by alpha into alpha cos alpha minus sine alpha by alpha square is equal to 0. Okay, as sine alpha is equal to 0, okay, as sine alpha is equal to 0, that is a minimum maximum, okay na, secondary maximum. So as sine alpha tends to 0, then alpha cos alpha minus sine alpha also tends to 0. So finally we can draw a conclusion that alpha is equal to sine alpha by cos alpha. So sine by cos leads to tan. So finally we will get alpha is equal to tan alpha. Okay, so alpha can be expressed as the tan is there, so it can be expressed as alpha is equal to plus or minus 3 pi by 2 or odd multiples 5 by 2 plus or minus 5 pi by 2. Okay, so this will be the secondary maximum. Then third one, minimum intensity radiation. So for the minimum intensity, as the sine alpha is equal to 0, so that is sine alpha is equal to sine plus or minus n pi. Okay, sine plus or minus n pi, right? So then alpha is equal to plus or minus alpha plus or minus 2 pi and plus or minus 3 pi. Okay, all the integral multiples of pi with the positive and the negative signs. So then finally we can conclude this essay question by the intensity distribution, how the intensity will be distribution among the single slit. So this is a pictorial or a graphical representation of the intensity distribution. So here we can clearly observe that how the intensity is going to be vary with the alpha. So the diffraction pattern what we are seeing by using the Fraunhofer diffraction by using a single slit. Okay, these consist of central principal maxima, okay now secondary maxima, and of decreasing intensity and minima. Okay, so all these three conditions can be represented by using this graph. Okay, so one can be observed that the graph that subsidiary maxima do not fall exactly midway between two minimas. Okay, so this is a single slit Fraunhofer diffraction due to the single slit. Okay.